Kali ini kita akan membahas tentang internet. Video pembelajaran ini digunakan untuk menuntaskan unit teknik jaringan dan internet, kemudian untuk KD mengenal jaringan komputer, lebih teknis lagi. Pembelajaran ini digunakan di kelas 9 semester 1 SMP Negeri 1 Kabupaten Magelang. Ibu membuat karya dengan memperkenalkan beberapa video dari internet dengan bahasa asing dari bahasa Inggris supaya menambah pemahaman kalian berkaitan dengan pembelajaran kita tentang internet. Ada 5 video di sini, terdiri dari
What is the Internet? History of the Internet. How does the Internet actually works? The Internet, cables, wires, and Wi-Fi. The Internet, IP address, and DNS. What is the Internet? Menjelaskan perkembangan internet dari tahun 1970 dan kondisi perkembangan internet yang dapat dinikmati dan dikembangkan lebih baik lagi untuk masa sekarang ini. History of the Internet menjelaskan tentang komunikasi data komputer dari tahun 1957, mulai dari perkembangan batch processing hingga time sharing system, kemudian menjelaskan tentang protokol NCP yang kemudian digantikan oleh TCP. How does the Internet actually works? Mengilustrasikan konsep komunikasi data dalam komputer hingga muncul istilah packet switching. The Internet, wires, cable, and Wi-Fi menjelaskan tentang konsep bits dalam transfer data, pengukuran kecepatan data dalam bit rate, bandwidth, dan latency, serta konsep perkembangan media yang digunakan dalam internet. The Internet, IP address, and DNS mengilustrasikan standarisasi komunikasi data, konsep IP address dalam versi IPv4 dan IPv6, serta konsep DNS hingga kegiatan DNS spoofing yang merugikan. Video pembelajaran ini juga disertai dengan lembar kerja yang dapat kalian unduh di alamat berikut ini. Jangan lupa like, komen, dan subscribe. Selamat menikmati.
What is the internet?
The internet is like a popular thing.
Some satellites up there.
I picture in my head with like waves of internet going to the phone.
Somebody told me a cloud once.
The internet is a lot like plumbing. It's always moving.
Most people don't have any idea where the internet came from, and it just doesn't matter. They don't need to. It's sort of like asking who invented the ballpoint pen or the flush toilet or, the zipper. These are all things we just use every day, and we don't even think about the fact that one day somebody invented them. So the internet is just like that. Many, many years ago, in the early 1970s, my partner Bob Kahn and I began working on the design of what we now call the internet. It was a result of another experiment called the ARPANET, which stood for Advanced Research Projects Agency Network. It was a Defense Department research project. Paul Barron was trying to figure out how to build a communication system that might actually survive a nuclear attack. So he had this idea of breaking messages up into blocks and sending them as fast as possible in every possible direction through the mesh network. So we built what eventually became a nationwide experimental packet network, and it worked. Is anybody in charge of the internet?
The government controls it.
Elves, obviously elves.
The people who control the Wi-Fi, because then no Wi-Fi, no internet. T-Mobile, Xfinity.
Bill Gates.
Bill Gates.
Bill Gates. Right?
The honest answer is, well, nobody, and maybe another answer is everybody. The real answer is that the internet is made up of an incredibly large number of independently operated networks. What's interesting about the system is that it's fully distributed. There's no central control that's deciding how packets are routed or where pieces of network are built or even who interconnects with whom. These are all business decisions that are made independently by the operators. They are all motivated to assure that there is end-to-end connectivity of every part of the network, because the utility of the net is that any device can communicate with any other device, just like you want to be able to make phone calls to any other telephone in the world. There's nothing like this that has ever been built before. The idea that what you know might be useful to somebody else or vice versa is a very powerful motivator for sharing information. By the way, that's how science gets done. People share information. So this is an opportunity for people to think up new applications, maybe program them as apps on a mobile phone, maybe become part of the continued growth of the infrastructure of the network to bring it to people that don't have access to it yet, or just make use of it on a day-to-day basis. You can't escape from contact with the internet, so why not get to know it and use it?
The Internet, in the year 2009. We send emails, make calls over the Internet, and discuss topics we take an interest in. Even our banking is going virtual. But what we take for granted today was only a vague idea 50 years ago. In order to understand how we got this far, let's go back to 1957, when everything began. Before 1957, computers only worked on one task at a time. This is called batch processing. Of course, this was quite ineffective. With computers getting bigger and bigger, they had to be stored in special cooled rooms. But then the developers couldn't work directly on the computers anymore. Specialists had to be called in to connect them. Programming at that time meant a lot of manual work, and the indirect connection to the computers led to a lot of bugs, wasting time and fraying the developers' nerves. The year 1957 marked a big change. A remote connection had to be installed so that the developers could work directly on the computers. At the same time, the idea of time sharing came up. This is the first concept in computer technology to share the processing power of one computer with multiple users. On October the 4th in 1957, during the Cold War, the first unmanned satellite Sputnik 1 was sent into orbit by the Soviet Union. The fear of a missile gap emerged. In order to secure America's lead in technology, the US founded the Defense Advanced Research Project Agency in February 1958. At that time, knowledge was only transferred by people. The DARPA planned a large-scale computer network in order to accelerate knowledge transfer and avoid the doubling up of already existing research. This network would become the ARPANET. Furthermore, 3 other concepts were to be developed, which are fundamental for the history of the Internet. The concept of a military network by the RAND Corporation in America. The commercial network of the National Physical Laboratory in England. And the scientific network Cyclades in France. The scientific, military, and commercial approaches of these concepts are the foundations for our modern Internet. Let's begin with the ARPANET, the most familiar of these networks. Its development began in 1966. Universities were generally quite cautious about sharing their computers. Therefore, small computers were put in front of the mainframe. This computer, the interface message processor, took over control of the network activities, while the mainframe was only in charge of the initialization of programs and data files. At the same time, the IMP also served as interface for the mainframe. Since only the IMPs were interconnected in a network, this was also called IMP subnet. For the first connections between the computers, the Network Working Group developed the Network Control Protocol. Later on, the NCP was replaced by the more efficient Transmission Control Protocol. The specific feature of the TCP is the verification of the file transfer. Let's take a short detour to England. Since the NPL network was designed on a commercial basis, a lot of users and file transfer were expected. In order to avoid congestion of the lines, the sent files were divided into smaller packets, which were put together again at the receiver. Packet switching was born. In 1962, American Ferret aircraft discovered middle and long-range missiles in Cuba, which were able to reach the United States. This stoked fear of an atomic conflict. At that time, information systems had a centralized network architecture. To avoid breakdown during an attack, a decentralized network architecture had to be developed, which, in case of loss of a node, would still be operative. Communication still used to work through radio waves. That would have caused problems in case of an atomic attack. The ionosphere would be affected and the long-wave radio waves wouldn't work anymore. Therefore, they had to use direct waves, which, however, don't have a long range. A better solution was the model of a distributed network. Thus, long distances could be covered with a minimum of interference. Another milestone followed with the development of the French network Cyclades. Since Cyclades had a far smaller budget than ARPANET, and thus also fewer nodes, the focus was laid on the communication with other networks. In this way, the term Internet was born. And the International Organization for Standardization designed the OSI reference model. The innovation of OSI was the attempt to standardize the network from its ends, and the channel's division into separate layers. Finally, the TCP assimilated the preferences of the OSI reference model and gave way to the TCP/IP protocol, a standard which guaranteed compatibility between networks, and finally merged them, creating the Internet. By February the 28th, 1990, the ARPANET hardware was removed. But the Internet was up and running.
Have you ever wondered how the internet actually works? When you're chatting on your smartphone with grandma, or playing an online video game, or sending an email to a friend, the internet can feel like magic. But understanding how the internet works is critical, especially when policymakers are considering net neutrality rules that could dramatically change our internet experience. So let's go deep inside the internet and take a look at what's actually happening. Internet traffic is divided into parcels of data called packets. The packets split apart when you hit send and come back together when they arrive at their destination. These packets are converted into pulses of light or radio signals that travel through a cable to a device called a router. The router sends the packets along to their destination. It operates something like a conveyor belt sorting luggage at an airport. When there's no congestion, these packets move to their destination without difficulty or delay. But what happens when there are too many packets moving through a junction at a given moment in time? Let's say an email hits a bottleneck. Random packets will drop and try again a few milliseconds later when it's their turn at the junction. Your email may be delayed a second or two, but for most of us, that's no big deal. But what happens when real-time traffic like a video chat or voice call hits the same bottleneck? If packets are dropped, you may be disconnected. The voice may be garbled. The video may be jittery. There may be a delay or an echo. The experience is incredibly frustrating. And this is even more of a challenge when speed matters, like with fast-paced stock trading or online video gaming, as well as with new applications like real-time health monitoring. If the packets aren't reassembled at their destination just at the right time, just in the right order, the applications won't work properly. Fortunately, there's a way to avoid the vast majority of these problems, and that's through scheduling of internet traffic. By labeling packets and making the sorting devices understand which packets need to go where and when, everyone's experience gets better. Scheduling of internet traffic allows for real-time applications to be routed first, while other applications can be sorted as space becomes available. Scheduling also opens possibilities for consumers who want specialized experiences, like fast-paced stock trades or online video gaming, that can be provided without impacting the experience of other consumers. Now, is there a role for government in all of this? Absolutely. To stop or punish bad acts. Blocking of legal content is wrong, and anti-competitive behavior should be investigated by regulatory authorities. But without the ability to schedule, which helps prioritize traffic when necessary, our internet experience won't be as good as it can be. Policymakers are deciding how flexible or restrictive net neutrality regulations will be. The fact is, not all bits are created equal. If we treat them that way, consumers will pay the price, and they won't have access to innovative new technologies and services that have the power to improve our internet experience.
My name is Tess Swinlock. I'm a software engineer at Google. Here's a question. How does a picture, text message, or email get sent from one place to another? It isn't magic. It's the internet, a tangible physical system that was made to move information. The internet is a lot like the postal service, but the physical stuff that gets sent is a little bit different. Instead of like boxes and envelopes, the internet ships binary information. Information is made of bits. A bit can be described as any pair of opposites, on or off, yes or no. We typically use a 1 meaning on or a 0 meaning off. Because a bit has two possible states, we call it binary code. 8 bits strung together makes 1 byte. 1,000 bytes all together is a kilobyte. 1,000 kilobytes is a megabyte. A song is typically encoded using about 3 to 4 megabytes. It doesn't matter if it's a picture, a video, or a song, everything on the internet is represented and sent around as bits. These are the atoms of information. But it's not like we're physically sending ones and zeros from one place to another, one person to another. So what is the physical stuff that actually gets sent over the wires and the airwaves? Well, let's look at a small example here of how humans can physically communicate to send a single bit of information from one place to another. So say that we could turn on a light for a 1 or off for a 0, or use beeps or similar sort of things of like Morse code. These methods work, but they're really slow, error-prone, and totally dependent upon humans. What we really need is a machine. So throughout history, we've built many systems that can actually send this binary information through different types of physical mediums. Today, we physically send bits by electricity, light, and radio waves. To send a bit via electricity, imagine that you have 2 light bulbs connected by a copper wire. If one device operator turns on the electricity, then the light bulb lights up. No electricity, no light. If the operators on both ends agree that light on means 1 and light off means 0, then we have a system for sending bits of information from one person to another using electricity. But we have a problem. Let's say that, we want to send 5 zeros in a row. Well, how can you do that in such a way that either person can actually count the number of zeros? Well, the solution is to introduce a clock or a timer. The operators can agree that the sender will send 1 bit per second, and the receiver will sit down and record every single second and see what's on the line. To send 5 zeros in a row, you just turn off the light. Wait 5 seconds, the person on the other end of the line will write down all 5 seconds, say 0, 0, 0, and for ones, do the opposite, turn on the light. Obviously, we'd like to send things a little bit faster than 1 bit per second, so we need to increase our bandwidth, the maximum transmission capacity of a device. Bandwidth is measured by bit rate, which is the number of bits that we can actually send over a given period of time, usually measured in seconds. A different measure of speed is the latency, or the amount of time it takes for 1 bit to travel from one place to another. from the source to the requesting device. In our human analogy, 1 bit per second was pretty fast, but kind of hard for a human to keep up with. So let's say that you want to actually download a 3 megabyte song in like 3 seconds. At 8 million bits per megabyte, that means a bit rate of about 8 million bits per second. Obviously, humans can't send or receive 8 million bits per second, but a machine can do that just fine. So if we really want this internet thing to work over the entire world, we need a different way of sending this information really long distances. I mean, like across an ocean. So what else can we use? Well, what do we know that moves a lot faster than just like electricity through a wire? Well, light. We can actually send bits as light beams from one place to another using a fiber optic cable. A fiber optic cable is a thread of glass engineered to reflect light. When you send a beam of light down the cable, light bounces up and down the length of the cable until it is received on the other end. Depending on the bounce angle, we can actually send multiple bits simultaneously, all of them traveling at the speed of light. So fiber is really, really fast. But more importantly, the signal doesn't really degrade over long distances. This is how you can go hundreds of miles without signal loss. This is why we use fiber optic cables across the ocean floors to connect one continent to another. In 2008, there was a cable that was actually cut near Alexandria, Egypt, which really interrupted the internet for most of the Middle East and India. So we take this internet thing for granted, but it's really a pretty fragile physical system. And fiber is awesome, but it's also really expensive and hard to work with. But how do we move things without wires? How do we send things wirelessly? Wireless bit sending machines typically use a radio signal to send bits from one place to another. The machines have to actually translate the ones and zeros into radio waves of different frequencies. The receiving machines reverse the process and convert it back into binary on your computer. So wireless has made our internet mobile, but a radio signal doesn't travel all that far before it completely gets garbled. Great as wireless is, today it still relies on the wired internet. If you're in a coffee shop using Wi-Fi, then the bits get sent through this wireless router and then are transferred to the physical wire to travel the really long distances of the internet. The physical method for sending bits may change in the future, whether it's lasers sent between satellites or radio waves from balloons or drones, but the underlying binary representation of information and the protocols for sending that information and receiving that information have pretty much stayed the same. Everything on the internet, whether it's words, emails, images, cat videos, puppy videos, all come down to these ones and zeros being delivered by electronic pulses, light beams, radio waves, and lots and lots of love.
Hi, my name is Paula, and I am a software engineer at Microsoft. Let's talk about how the internet works. My job relies on networks being able to talk with one another. But back in the 1970s, there was no standard method for this. It took the work of Vint Cerf and Bob Kahn to invent the Internet Working Protocol to make communication possible. This invention laid the groundwork for what we now call the Internet.
The Internet is a network of networks. It links billions of devices together all around the globe. So maybe you're connected with a laptop or a phone through Wi-Fi, but then that Wi-Fi connection connects to an Internet Service Provider, or ISP, and that ISP connects you to billions and billions of devices around the world through hundreds of thousands of networks that are all interconnected. One thing that most people do not appreciate is that the Internet is really a design philosophy and an architecture expressed in a set of protocols. A protocol is a well-known set of rules and standards that, if all parties agree to use it, will allow them to communicate without trouble. All the different devices on the Internet have unique addresses. An address on the Internet is just a number, similar to a phone number or a sort of street address that's unique to each computer or device at the edge of the network. Of one of the most important protocols used in Internet communication, simply called the Internet Protocol, or IP. A computer's address then is called its IP address. Visiting a website is really just your computer asking another computer for information. Your computer sends a message to the other computer's IP address, and it also sends along its origin address so the other computer knows where to send its response.
You may have seen an IP address. It's just a bunch of numbers. These numbers are organized in a hierarchy. Just like a home address has a country, a city, a street, and a house number, an IP address has many parts. Just like all digital data, each of these numbers is represented in bits. Traditional IP addresses are 32 bits long, with 8 bits for each part of the address. The earlier numbers usually identify the country and regional network of the device. Then come the subnetworks, and then finally the address of the specific device. This version of IP addressing is called IPv4. It was designed in 1973 and widely adopted in the early 80s and provides for more than 4 billion unique addresses for devices connecting to the internet. But the internet has turned out to be much more popular than even Vint Cerf imagined, and 4 billion unique addresses won't be enough. We're now in the middle of a multi-year transition to a longer IP address format called IPv6, which uses 128 bits per address and provides over 340 undecillion unique addresses. That's more than enough for every grain of sand on Earth to have its own IP address.
Most users never see or care about internet addresses. A system called the Domain Name System, or DNS, associates names like www.example.com with the corresponding addresses. Your computer uses the DNS to look up domain names and get the associated IP address, which is used to connect your computer to the destination on the internet.
And it goes a little something like this.
Hey, hi there. I want to go to www.code.org.
Yeah, I don't know the IP address for that domain. Let me ask around. Hey, you know how to get to code.org?
Yeah, I got it right here. It's 174.129.14.120.
Oh, okay, great, thanks. Yeah, I'm gonna write that down and save it for later in case I need it. Hey, here's that address you wanted.
Awesome, thank you.
So how do we design a system for billions of devices to find any one of billions of different websites? There is no way one DNS server can handle all the requests from all devices. The answer is that DNS servers are connected in a distributed hierarchy and are divided into zones, splitting up responsibility for the major domains, such as .org, .com, .net, etc. DNS was originally created to be an open and public communication protocol for government and educational institutions. Because of its openness, DNS is susceptible to cyber attacks. An example attack is DNS spoofing. That's when a hacker taps into a DNS server and changes it to match a domain name with the wrong IP address. This lets the attacker send people to an imposter website. If this happens to you, you are vulnerable for more problems because you are using that fake website as if it is real. The internet is huge and getting bigger every day, but the domain name system and internet protocol are designed to scale, no matter how much the internet grows.